Okay guys, here we go. We're going to take a look at some complex numbers here. And before we get actually talking about that, let's take a look at a number line here. So let's take a look at this number line and let's just start throwing out some numbers and see how they fit on the number line. So I'm going to start with the most obvious number, 0. 0 we can put in the middle of the number line. Let's try a number like this. Where would 4.398 go? Go somewhere there, be to the right of 0. If we think about pi, could pi go on a number line? Well, pi is around 3.14. So it would be to the left of 4.398, somewhere there. Let's think of a number smaller than pi and greater than 0. I don't know, root 2. Root 2 is around 1.4 something. But either case, we know it would go in between pi and 0. Let's try some negative numbers, maybe like negative 9/8. And we could even take a look at a number like this, negative root 97, noticing, right guys, noticing that that negative is on the outside there. That's going to be an important distinction we'll make in a minute. Negative root 97. The question is, we know, what do all these numbers have in common though? All these numbers have in common, they are all real numbers. Okay, what do we mean by real numbers? Well, to put it as simply as possible, they all can be ordered on a number line. And that's really important. It sounds kind of obvious. They can all be ordered on a number line. Again, that seems really obvious, but it makes sense. We have a way to order them, right? We have a way to order them from smallest to largest. If we can fit it on a number line, if we know where they fit in relationship to other numbers, it's a real number, okay? So if we scroll down now a little bit, okay, I say quiz time. It's not really a quiz, but I do want you to try to go through these 6 problems as fast as you can. I might give yourself, 60 seconds. Try working through these 6 in 60 seconds, hit pause, work on them for 60 seconds, and then come back and we'll see how our answers are. See how we match. Okay, hopefully you did all right. Let's run through these really quick. 5 plus 8. 5 plus 8 here. Okay, 13. 11 times 4. 44. Negative 5 squared. Notice that negative is on the inside of the parentheses. Right, inside of the parentheses, that means we're squaring negative 5, and when you square a negative number, it becomes positive. So we have 25. 5 squared is also 25. The square root of 25 is going to be 5. Square root of negative 25, however, let's think about that. We can't have a square root underneath the radical, right? So what have we said previously to this? Okay, or what have you said in the past before you had learned about imaginary numbers? We've said it's impossible. And in fact, it is impossible, okay, using real numbers. Okay, that doesn't mean it's impossible. It just means using real numbers, it is impossible. You cannot take the square root of a negative number. And that's something you've seen over and over, especially the last few years, okay? So, let's go down, and as I said, there are no real number solutions to problem 6 on that previous page, but there are solutions, okay? And what people much smarter than myself came up with, they said, okay, I can't solve root negative 25 using our normal number set. Let me make up an imaginary number. So they made up an imaginary number. They really only made up 1. And they said, we're going to think of root negative 1, and we're going to call root negative 1 I. I is just going to stand for the square root of negative 1. Now really, what does that mean? In the real number world, it means nothing. That's why it's called an imaginary number. But in the imaginary number world, I is equivalent to root negative 1. Okay, it's equivalent to root negative 1. So if we understand that idea, that it's kind of this imaginary made-up idea that root negative 1 is just equal to I, or I is equal to root negative 1, we can do some things with it. So let's take a look at this problem again, the square root of negative 25. And let's remember from algebra 1, or algebra 2 I should say, that the square root of a times the square root of b is equal to the square root of a times b. Right, so you saw something, let's just maybe review real quick. You might have saw something like root 8, and you might have broken that down into root 4 times root 2 and said that simplifies to 2 root 2. That might be how you saw it before. Let's take a look at root 25, though. Negative 1 into 25, excuse me. What could I break that down into? Well, it would make sense, right, that I could break this down into two numbers as well. What if I broke it down into root 25 times root negative 1? Well, what's the square root of 25? Well, we saw above, and we should know that the square root of 25 is 5. What's the square root of negative 1? Well, we defined that before as I. So we could call that I, and we could kind of come up with this idea that the square root of negative 25 is equal to 5i. Again, in real number world, that doesn't mean anything, but in imaginary land, which is where we are now, it does give us an answer. It does give us 5i. Okay, so that's kind of the idea behind these negative numbers here. So let's run through a few of these fairly quickly. Square root of negative 2, how could we simplify that? Well, it would simplify, right, to root negative 1 times root 2. Always factor out that root negative 1 first. And all of these problems, we're going to factor out the root negative 1 first and then simplify. It'll make more sense in a minute. But let's take a look at this. Root negative 1 we know is I. Root 2 is just root 2. So we can say that number 1, root negative 2, simplifies to I root 2. Let's take a look at number 2, and let's get back to what I was talking about before, a second ago. Before you start breaking anything down into these trees, let's always factor out the root negative 1, and you'll see why. Okay? So we have root negative 1 times root 8. We know root negative 1 is I, but root 8 can be simplified into root 4 times root 2. We'll carry down the I again. Root 4 we know to be 2. Okay? And we also know root 2 is just left as root 2. So I have I times 2 times root 2, which if we write it all together, it would be I 2 root 2. Again, I think the number one thing I'd want you to take from this video, besides the idea of what I is that when you are factoring out or simplifying, you always need to factor out the root negative 1 first. Really critical that we understand that. Root negative 9, I'll let you do that on your own if you want to. It's pretty straightforward. I squared, another one I'm curious about. What is I squared? Well, if we break I squared down, it's really I times I. Okay, hopefully that makes sense. I squared is I times I. And I is root negative 1 times root negative 1. And you may be thinking, well, what's that equal to? Is it equal to positive 1? Well, let's go back to this property you might have seen before. I'll just write it to the left here. Root 3 times root 3 is equal to root 9, which we know is just equal to 3. Okay, root 4 times root 4 is equal to root 16, which is equal to 4. And let's do one more. Let's say root 5 times root 5 is equal to root 25, which is equal to 5. So what do you notice in the pattern here? Well, we notice when we multiply two roots together of the same number, it just becomes a number underneath. So root 3 times root 3 was regular 3. Root 4 times root 4 was regular 4. Root 5 times root 5 was regular 5. So what do you think root negative 1 times root negative 1 is going to be? Well, it's just going to be the number underneath the radical. It's just going to give me negative 1. Now notice an important point there. I multiplied two imaginary numbers together, the two imaginary numbers being root negative 1 and root negative 1, and what happened? Did it become a real number? Well, root negative 1 fits on a number line, so yes, it did. Which is a really interesting point, and something big you need to take from this is that multiplying two imaginary numbers together like I times I, or I squared, results in a real number. Okay, results in a real number. So my only other homework for you besides the graphing problem you did before on polynomials is, ignore this for a second, we'll cover this tomorrow. Excuse me. Ignore this right here. Don't cross it out like me, but we're going to deal with it tomorrow. Is these rules for I. And let's run through the first 4, then I want you to come up with the next 4. What is I equivalent to? Well, I is root negative 1, or just I. I squared, as we saw before, is negative 1. What would I cubed be equal to? Well, let's come over here on the right. Well, I know I cubed. I could break it down into I squared times I. And I do know that I squared is -1. And I know I is I. What's -1 times I? Well, that would just simplify to -I. So what's I cubed? It's -I. And I to the 4th. Let's take a look at I to the 4th. If I take I to the 4th and I break that down into I squared times I squared, well, what's I squared? Well, we said before I squared is -1. So that's -1. That's -1. What's -1 times -1? Well, that is simply just +1. So I to the 4th is +1. So notice that when I got I, it was just I. When I squared I got a real number. However, when I cubed I, right, I went back to an imaginary number, yet when I raised I to the 4th power, it was back to being real. Okay, so notice that pattern. What I want you to do for homework to finish up is to figure out, or take a best guess, as to what I to the 5th is, I to the 6th, I to the 7th, and I to the 8th. Okay, I highly, highly, highly encourage you to try to draw some type of tree, break down I to the 5th, I to the 6th, I to the 7th, I to the 8th, using a tree, using numbers you know. Maybe you can break out an I to the 4th from one of these numbers, or an I squared, okay? And see if you can come up with what those four would be equivalent to, okay? That's the only remainder of your homework. We'll talk about it tomorrow in class, and that's it.